Hello everyone, welcome to Atoms and Sporks, and in this video I want to talk about what electrons are actually doing in something like an electrical wire. And along the way we'll learn that in order to understand such a simple, everyday thing, we're going to have to take a surprisingly deep dive into the world of quantum physics. Now, when I was in high school, I was taught that in something like a copper wire, you basically have something like a pinball game. You have the copper atoms, which are made of negatively charged electrons, which surround a positively charged atomic nucleus. And in something like a metal, I was taught that they've kind of come apart. They've given up some free electrons, which are little pinballs, and what's left is a charged ion. And these ions are sort of fixed in place in a ordered and repeating lattice. We say metal has a crystalline lattice. And these free electrons form a kind of gas, very much like the air molecules in a room. And finally, the two interact, with the ions acting like kind of pinball bumpers, and the electrons like pinballs constantly scattering off of them. And when they do collide, it randomizes the electron speed and direction. So it's a hot gas of our little electron pinballs, and they're constantly smacking into these ionic cores that act like pinball bumpers. The final key ingredient is that a pinball machine is tilted. When we say we're applying a voltage to an electrical wire, what that actually means is that we're basically pegging one end of the wire to be a different electrical potential energy than the other end. Well, in our pinball machine, if we tilt the machine, that means that one end is at a different gravitational potential energy than the other end. So the analogy is actually pretty good. In both a pinball machine and an electrical wire, one end is being held at a different potential energy than the other. All that's different is the specific type of potential energy. And in both cases, this gradient results in a force. Our pinballs accelerate downhill, pushed by gravity and the tilt, just like our electrons are accelerated and pushed by the electric field that arises when we apply the voltage. So that's basically the model I was taught in high school, and the nice thing about it is that it gives a very clear intuition about what determines how conductive a metal is. It's all about these bumpers and their randomizing effect. If there were no bumpers, if there were no ionic cores, then the electrons would just perpetually accelerate to incredible speeds as they are pushed by the electric field. But because of the bumpers, things don't go so well, and they're constantly scattered and their direction and speed randomized. It's all very intuitive, but is that intuition actually correct? For example, if it's the randomizing effect of these ionic core bumpers that's impeding current flow, then we obviously expect that the more bumpers there are, in other words, the more dense a material is, the lower its conductivity should be. More things to hit per unit volume means flow is more difficult. Seems pretty straightforward. Except, if I actually were to plot the density of various metals versus their conductivity, I actually don't see any negative trend. In fact, I don't really see any trend at all. So in that case, this model may be intuitive, but it gives the wrong intuition. As another example, this model gets pretty much everything wrong about how metals and insulators respond to heat. This idea it has where an insulator is kind of like a rigid array of little oscillating atomic cores, where a metal is a similar array plus this sort of free gas of electrons, well, that actually makes some very specific and bold claims when you walk it through the physics and math of thermodynamics. For example, it makes a very clear prediction on how the electrical conductivity should increase with temperature. And yeah, it is not right about that. Also, if it were true, it would mean that metals could actually store dramatically more heat than insulators. What's called their heat capacity would be very high. And no, that's not true either. And that's really just the tip of the iceberg. This pinball model not only quantitatively fails in all sorts of ways, but the intuition it builds gives the wrong qualitative understanding in lots of cases as well. So given that, I think a very good question to ask is, why is this model even taught in high schools in the first place? Well, this actually was a real model. It's called the Drude model, and it was set down in the year 1900, so well over a century ago. It's so old, in fact, that it predates quantum physics entirely. That's really, I think, the main reason it's still taught. A lot of high school curriculums cover physics chronologically, and it was indeed a model at one time. And then you have the side benefit that you just get to ignore quantum physics entirely, which is always a headache. But another reason is that it turns out you can actually heavily modify this model to include some aspects of quantum physics. We call this modern upgraded version the semi-classical Drude model. Semi-classical meaning part classical, part quantum mechanical. And this modified semi-classical Drude model is very powerful. And if you're wondering why we don't just always use a fully quantum mechanical model, well, in terms of physics simulation and intuition, such semi-classical models are often a lot more pragmatically useful than a full quantum treatment. So that's really another reason why it's still taught, because there is a completely reworked and upgraded form of this Drude model that is still used by physicists today. But then how different is this reworked semi-classical Drude model? Well, for example, there really are these sorts of periodic arrangements of ionic cores, and there really are sort of dissociated electrons that have decoupled from individual atoms. And it really is all about how these dissociated electrons scatter. That's all stuff that remains true. However, what it gets wrong is what these electrons really are and what it is they're hitting. They're very different from free electrons, and it's not the ionic cores that scatters them. So let's put our quantum physics hats on and try to understand what's really going on. If I were forced to sum up quantum physics in just one sentence, I wouldn't waste it talking about Schrödinger's cat or local realism paradoxes. Instead, I'd simply say that particles, like electrons, aren't little billiard ball-like things, but rather wavy things that do all sorts of regular wave stuff. And really, a lot of the mysterious reputation surrounding quantum physics just comes down to people not really being familiar with how waves, any waves, behave. For example, if I have a vibratable string and I clamp it down at 2 points, I find that between those points, I only have certain allowed states with certain frequencies that can exist. They're discrete harmonics created by confining a wave. That's exactly how something like a guitar works, or really any musical instrument. You confine a wavy vibrating system and thus force it to only allow certain discrete frequencies or pitches. And in quantum physics, electrons do this too. A free electron, just like any free wave, can have any energy or wavelength it likes. But electrons are negatively charged particles, and protons in the atomic nuclei are positively charged particles. And, well, oppositely charged particles exert an attractive force on one another. So as a nuclei pulls on an electron electromagnetically, there are two possibilities. Either the electron has enough energy to not be trapped by this pull, its initial speed is fast enough that it can avoid being caught, or it isn't, and it becomes held and confined. We say there are free states and bound states, which means it's formed an atom. And in one of those bound states, only certain energies can exist, just like our guitar string. But a solid material, like a piece of copper, isn't made of just one atom. It's made of trillions and trillions of them in a kind of repeating array. To see what happens there, let's look at a somewhat simpler case of just 3 atoms in a repeating pattern. What we see is that where one atom, there were discrete states with large spacings and energy separating them. With many atoms, we have more states, but they actually seem to sort of cluster into sets, where within each cluster, there's just a bunch of allowed energy states with only very small differences in energy. We also noticed something interesting. There are kind of 2 different classes of clustered states. There's those whose energy is less than one electron would need even to leave one atom, and therefore it's really trapped and associated with just one atom. But there's also these states here that don't have enough energy to be completely free of the solid, but do have enough energy to leave the pull of any one particular atom. These are called delocalized states, or sometimes Bloch electrons, because of something called Bloch's theorem in quantum physics that describes their behavior. And these delocalized or Bloch electrons are what's important to us. And notice that they have very little in common with the free electrons assumed by the Drude model. But of course, that's just 3 atoms in a line. And as I said, there are actually trillions upon trillions of atoms in a copper wire. However, all that happens when I add more and more atoms is that these clusters of energy states become more and more crowded. And in fact, the energy difference between states in these clusters becomes so small that we can really just kind of think of things as a continuous band of allowed states. And actually, it's these bands and the gaps between them that determine whether a given material is a metal or an insulator. In a metal, these sorts of delocalized states are occupied by electrons, where in insulators, for reasons we'll leave for another time actually, it's really only these states that are filled, and a big chunk of energy must be given to electrons in order to excite them to these conducting states. This is also why insulators like glass are transparent. The photons that make up visible light simply don't have the minimum amount of energy needed to excite an electron to one of these states in the upper band, and so such photons simply aren't absorbed because there's no possible energy jumps that could be done with their energy. So what determines whether something is a metal or not is not so much the atoms in isolation, but rather the shape and nature of this lattice it forms and the nature of these bands of states that result. So in our modernized semi-classical Judah model, the thing that is moving isn't free electrons, but rather these delocalized block electrons. That's the basic thing carrying charge around. And what are they scattering off of? Well, it's not the ionic cores. Remember, it was the effect of these cores that led to these states to begin with. In essence, when we talk about these delocalized electrons, we've already taken the effect of the ions into account. As a result, one of these delocalized electrons in one of these delocalized states in a perfect crystal lattice won't scatter at all. It's completely oblivious to the ionic cores because, like I said, in essence, their effect is already baked into the state it's in. So then what are these block electrons scattering off of? Well, there are two main sources. The first is simply defects and impurities. If one of these atoms is missing, or it's replaced with a different type of atom, then when one of these delocalized electrons passes by, its state gets distorted, because it's not the regular periodicity it's supposed to be. And that distortion is what we call scattering. The second important thing it scatters off of is what are called lattice waves, or acoustic waves, or phonons. Like we said, when we have a perfect lattice where every atom is in its correct place, then the natural state of being for an electron is one of these delocalized states. However, such a thing only actually happens at absolute zero, the coolest possible temperature. Otherwise, in reality, these ionic cores can randomly thermally move and oscillate, push and pull on their neighbors, kind of like a network of springs. And it's these lattice waves that our electrons are scattering off of. Though clearly the term scattering means something very different here, neck deep in a quantum description, than what we're maybe used to. Both our block electrons and our lattice waves are delocalized things. They can't really be said to be anywhere. They're completely spread out. And that's quite a bit different than our pinball and bumper analogy. It's more like two waves playing off of each other as they share the same space. And really, that's kind of what we mean. In the most general way, what we mean by scattering is that energy and momentum is being traded between these two subsystems, and as a result, the state of electrons are changed by the presence of the lattice waves. So it may not be as simple to visualize as a pinball and a bumper, but the ultimate outcome is the same. And that's our half-classical, half-quantum picture of what electrons are really doing in a wire. Let's recap. The basic object isn't a gas of free electrons, but rather the electrons are in these quantum mechanical delocalized block states. And these states have the effect of the interaction between the electrons and the lattice already baked into them, and thus they kind of ignore the ionic cores entirely. So unless there's either some defects or impurities, or heat energy has caused the cores to collectively, as one, oscillate, and thus their positions are different from their equilibrium positions, there is no scattering. No pinball at all. However, when you do have these lattice wave oscillations, they lead to an exchange of energy and momentum between our electrons and the ionic cores and randomize the electron motion. So, as is a regular theme on this channel, quantum physics is at the very heart of all kinds of everyday things. And really, the lives of electrons, just something simple like a copper wire, are far more different than we are often taught in high school. Hope you guys enjoyed the video. Please like and subscribe if you did. Have a good one.